Hello friends, today we are going to do matched filter in the stochastic processes. So before we start doing matched filters or derive the equation for that, we just need to know the Cauchy-Schwarz inequality, which states that where fx and gx are two random processes, so the integration of fx gx mod square is less than equal to the multiplication of individual mod square integration of both the processes, that is integration fx dx with respect to x square mod square is less than equal to mod fx square integration with respect to dx and mod gx square integration with respect to dx. And as this is an inequality and we get the equality condition when f of x is equal to k multiplied by k multiplied with g conjugate of x, that is conjugate of gx, that is if we multiply any constant with the conjugate of gx, then we get the equality conditions. So now we are going to start it is to derive our equations for the matched filter. Here okay, so this is the system and the input, let the input be any signal h of t along with the noise. Here S represents the signal and N represents the noise, and it is passed through a system with a function h of t. And now for designing the match filter, we have to find, we have to design the receiver so we get the best signal, which is that is on during the process we get the best signal at the output. So if we pass it through it, let us assume at this point the output is s cap of t plus wt. Here, here the output signal is, it is mixed with noise. So we can't say that we can't differentiate signal from the noise. That is that the signal is mixed with the noise or it is a complete noise. And for making our calculations easier, we assume that the noise is a white noise. So we are assuming that n of t is a white noise. So for any now we will calculate instantaneous signal to noise ratio at any instant of time t equal to t naught. So for any instant of time t equal to t naught, we calculate the signal to noise ratio. That is equal to mod s cap of t naught square divided by expected value mod of omega t square expected value of that. Here this, that is this right here, SNR output signal to noise ratio is s cap of t, that is finding at t equal to t naught is mod square divided by expected value of okay. Now this term, it means output signal at the time instant t equal to t naught, and this term represents average output noise power, average output noise power. Now we can write on expanding these terms. First I will write and then I will show how we get this on expanding them. We can write mod 1 upon 2 pi integration minus infinite to plus infinite s omega h omega e raised to the power j omega t d omega mod square divided by 1 upon 2 pi minus infinite to plus infinite sigma square or h omega square d omega. Here, let us say that we are applying any deterministic signal at the input. This is a deterministic signal, and the spectrum of the white noise, we can assume it is a, we know that the output power spectrum, spectral output power spectral density of white noise is a constant n, so we assume it to be here sigma square at any value, it is a constant sigma square. It is output spectral density of white noise. Now I will explain you how we get these terms, that is output signal at, how we get the value of output signal at the time instant t naught, and the average output noise power value. So output value of output signal, value of output signal at a time t, at any time t, this is equal to 1 upon 2 pi integration minus infinite to plus infinite s omega into h omega e raised to the power j omega t d omega. This is the this is the equation we need to solve it. So we simply put this equation in that uh, like I have placed before. Now we find the expected value of omega t. So this is nothing but equal to r w of 0. So this is nothing but the area under the, this is nothing but area under the power spectral density. So we can write like this as half, it is area under the power spectral density, can be written as 1 upon 2 pi integration output power spectral density, that is s the omega bracket omega with integration with respect to d omega. This is nothing but, okay, let me write it here, it is output power spectral density. And now we can write output power spectral density, that is s omega as, we can write it as the multiplication of input power spectral density, input power, I am writing PSD. Okay. Output power spectral density, I am writing short form power spectral, PSD for power spectral density. So I can write this as the multiplication of input power spectral density with the square of system transfer function. And now for the white noise, we have assumed that this is sigma square. So then we place it in the values in the equation like we have placed in the signal to noise ratio, we get this. I have written this equation earlier, and after that I have derived how we got these values. So I am writing again for your convenience, that is, this is the signal to noise ratio is equal to mod s cap t naught square divided by, okay, let me rub it and write it from the top again. So signal to noise ratio at any instantaneous time t equal to t naught, we get it as s cap t naught mod square divided by expected value of omega t mod square expected value. And now as I told you before this section, we get the equation. So directly placing the equations, we get mod 1 upon 2 pi minus infinite to infinite s omega h omega e raised to the power j omega t d omega mod square divided by 1 upon 2 pi minus integration with minus infinite to plus infinite sigma square mod h omega square d omega. And before starting the mesh filters, I told you about the Cauchy squares inequality. Using that, we can write this equation would be less than equal to 1 upon 2 pi sigma square integration minus infinite to plus infinite s omega h omega e raised to the power j omega t d omega square divided by integration minus infinite to infinite h omega square mod h omega square with respect to d omega. Now we can break the integration here, and on breaking and simplifying we get 1 upon 2 pi 1 upon 2 pi 1 upon 2 pi integration minus infinite to plus infinite, we get mod s omega square integration with respect to d omega into sigma square. And as this is a constant value, so we can replace it by for that is taking into consideration the this is an inequality, and to make it into equality we take some constant, so we replace it by e s upon sigma square. So now we get that this is the maximum signal to noise ratio. So this is that is we have derived the equation, the conditions for the matched filter when we get the maximum signal to noise ratio. And this is h omega, you can write like this as s omega into e to the power j omega t naught conjugate s conjugate omega into e to the power minus j omega t naught. And in the time domain, we can say that h of t is equal to s conjugate t minus t naught. That is, we can say from the uh, that is, if p of t is a stable white noise we have taken with sv omega equal to s, that is some constant value we have taken sigma square, we get the system function as h omega is equal to, we get this. That is, we can, I have proved that below before, is ht equal to k conjugate of e t minus t naught minus t. It is impulse response of the, we have got the impulse response of the matched filter. Now for the next claim 2, for the matched filter, next condition we need to prove is, that is, we are given that v of t is any arbitrary regular White's and stationary process with sv omega. Then we have to prove that the system function is h omega equal to k multiplied with conjugate of f omega upon sv omega into e raised to the power minus j omega t naught, and the corresponding signal to noise ratio, is 1 upon 2 pi integration minus infinite to plus infinite mod f omega square upon sv omega d omega. So now we are going to prove this claim. For this, we take this diagram into consideration. A signal is inputted to a system. Actually, this is a combined filter, and this term it is for whitening filter for V of t. This is, we can say, whitening filter for of V of t, and this is matched filter for the non-white noise. This is the matched filter for non-white noise. And okay, and we get after passing through this, the signal becomes, we get x1 of t equal to f1t plus iv of t, where this iv of t it is nothing but white noise with the spectral density iv, the spectral density 1. So, and we have chosen the value of this filter in such a way that siv omega is 1, that is nothing but sv of omega or sigma v square is equal to 1. So from this equation we can write that sv omega is equal to 1 upon mod sigma omega square. Now see, from claim 1, in the claim 1, that is in the previous case I have explained that at the end we can say that h1 omega is equal to a constant k into conjugate of f1 omega multiplied e raised to the power j omega t naught. So now we can write, so from here I am writing here, now we can write h omega as sigma v omega into h1 omega. Now putting the values of h1 omega from this equation that we derived in the first part, I will get, okay, I'll write it here, sigma v omega into k multiplied with conjugate of f1 omega multiplied with e raised to the power minus j omega t naught. So now we can get, now in solving we get this k conjugate of f naught omega to sigma mod sigma square e raised to the power minus j omega t naught. And now this we can write it like this, as this is from this equation we can replace this is equal to 1 upon sv omega. So from this we are getting sv omega into e raised to the power minus j omega t naught. So here we have got that when the given v of t is an arbitrary regular wide and stationary process with sv omega, the system function is h omega equals to k into conjugate of f omega multiplied with e raised to the power minus j omega t naught divided by sv omega. Now second we are required to find out the signal to noise ratio. Corresponding we are required to show that this is equal to this. So for the signal to noise ratio, okay, now from the first part we take that the corresponding signal to noise ratio is SNR equals to 1 upon 2 sigma square minus infinite to infinite integration mod f1 omega square respect to dw. But we have taken the value as in the starting when we apply the signal, we have taken that the power spectral density of the value of that is 1. So that is sigma square is equal to 1. So this equation is simply becomes square root of 1 divided by 2 pi integration minus infinite to plus infinite mod f1 omega square d omega. Now we can expand, and now we can write this as, just write to simply directly from the previous equation we solved. This is equal to sigma b omega square with respect to d omega. Now from that is from we can write value of this one is, value of this is, we know that sigma square mod sigma square into sv omega multiplied is equal to 1. So from this equation we can write it, put the value of sv, that is mod square mod of sigma omega is equal to 1 upon sv omega. So putting on this is that we get 1 upon 2 pi integration minus infinite to plus infinite f omega square into 1 upon sv omega d omega. So we get that for when the given signal is v of t, that is WSS signal with sv omega, then the required, then the corresponding signal to noise ratio at the output is 1 upon 2 pi integration mod square f omega into 1 upon sv omega square root of that. So in that we get the both the conditions for the matched filters, and we have proved that is first cases for the matched filter. In the second case, if we have proved that if we are taking any regular WSS process signal with that, so we can get the system function at any time instant this of this value, and the corresponding signal to noise ratio at the output we can get of this value. Thank you.